Ladies and gentlemen, friends, listening across the United States and around the world, welcome to Science to Sleep By. Tonight, we're going to drift gently into the calm waters of cosmic mystery, not to stir anxiety, but to quiet the mind with the slow, distant truths of the universe. Because sometimes, the best way to fall asleep is to listen to something bigger than our worries, something drifting silently among the stars. This is a Science to Sleep By exploration of one of the most misunderstood interstellar visitors ever detected, 3I Atlas, and the story behind why NASA took so long to release its images. A delay that, for some, felt like more than a delay. It felt like a secret. Tonight, we slow down, breathe, and unravel the mystery one gentle thread at a time. When we begin to speak about 3I Atlas, we are not just discussing another comet or asteroid drifting through the solar system. We are speaking about an object that came from a place far beyond the planets we know, beyond the Oort cloud, beyond the frozen outskirts of our own cosmic neighborhood. It is an interstellar traveler, meaning its birthplace lies in a completely different star system, a different gravitational cradle, a different cosmic history. And when something like that enters our skies, even for a moment, it becomes a story woven with wonder, suspicion, and the quiet awe that only deep space can inspire. To understand 3I Atlas, we first must imagine the scale of the space it crossed to get here. Our nearest star system, Alpha Centauri, sits more than 4 light-years away. A light-year is nearly 6 trillion miles, and this object may have traveled dozens or even hundreds of light-years before it ever brushed past the Sun. By the time we detected it, 3I Atlas was already tired, faint, and fragile, its long journey written into every molecule of its form. To a scientist, this makes it a messenger. To a dreamer, a visitor. To a skeptic, perhaps something else. But to everyone, it was a reminder that our solar system is not closed, not isolated, not shielded from the wider galaxy flowing around it. Back in 2017, humans first experienced what it felt like to witness an interstellar object, when one Oumuamua scratched through our space like a stone skipping across a pond. 2 years later came 2, Borisov, icy, blue, and unmistakably comet-like. But 3I Atlas, the third interstellar visitor ever recorded, carries a personality of its own. When astronomers at the Asteroid Terrestrial Impact Last Alert System Atlas first spotted it, there was an immediate sense of urgency. These objects move fast, accelerated by the gravitational tides of stars across the galaxy, and often slip through observation windows before we can fully study them. NASA and other space agencies rush to calculate its orbit, confirm its origin, and capture as many images as possible before its trajectory carried it out of reach. But 3I Atlas did not arrive with the pristine clarity we wish interstellar objects would provide. It arrived dim, fragmented, already shedding pieces of itself. It appeared like something that had survived enormous stresses in the interstellar medium, cosmic radiation, micrometeorite collisions, temperature extremes beyond imagination. It was a relic, but a fragile one, as if the long voyage had eroded its strength and muted its brightness. This made observing it profoundly difficult, and to the public, those early difficulties would soon fuel suspicion. What stands out about 3I Atlas is not just its origin, but its timing. It arrived during a moment when skepticism toward scientific institutions was rising. Many people wondered how something from another star system could be detected, photographed, and studied, yet the images were slow, delayed, trickling out in carefully processed releases. This delay created a tension between expectation and reality, between what people hoped to see and what astronomers were realistically capable of capturing. But before suspicion comes understanding, and before understanding comes the nature of the object itself. 3I Atlas was never a bright visitor. It never flared like a classic comet. It never presented a grand tail sweeping across the night sky. Instead, it was a faint smear of reflected sunlight, drifting so quickly and at such a great distance that even powerful observatories struggled to gather clean data. Yet that faintness is part of its beauty. Interstellar space is a harsh sculptor. and 3I Atlas were its scars like ancient writing. Its faint glow told astronomers that it had lost mass long before entering our system, perhaps breaking apart under gravitational tides, or suffering internal fractures caused by temperature differences so extreme they would tear steel apart. Nothing about this object was simple. Nothing was cinematic. It was subtle, quiet, almost shy, a visitor that did not want attention. Understanding 3I Atlas also means understanding that interstellar objects are not tourists or explorers. They are debris, fragments from worlds we will never see. They are pieces of planetary systems torn apart by collisions or gravitational chaos that launch them into the galaxy like wandering seeds. Some come from dying stars, others from young systems still forming planets. Each interstellar object carries a chemical story embedded in its structure, and 3I Atlas was no exception. Spectral analysis hinted at volatile ices, minerals, and organic compounds shaped by unfamiliar conditions. Its composition was not identical to comets native to our solar system, suggesting that the processes shaping other star systems imprint themselves onto even the smallest particles. When the first data trickled in, astronomers realized they were looking at something ancient, delicate, and irreplaceable. And that fragility is partly why imaging it took time. Every second mattered, every exposure had to be calibrated, every pixel scrutinized, because an object like this may never appear again in our lifetimes. At the same time, its journey itself adds to its enigmatic nature. Think of the space between stars as an ocean so vast and so empty that even a single grain of dust rarely completes a crossing. And yet this object, this fragment, this cosmic traveler, journeyed through that ocean untouched by any star's gravity until it passed close enough for our sun to tug it into a brief, looping trajectory. For a moment, just a moment, it became ours to observe. And when interstellar objects enter our system, they become mirrors for our imagination. They remind us how small we are, how enormous the galaxy is, and how little control we truly have over the cosmic events occurring around us. Some people marvel, some people fear, some question the institutions that present the data, but regardless of reaction, the object remains the same, silent, drifting, unaware of the stories being invented about it. 3I Atlas, in this way, is not just a scientific discovery, it is a catalyst for reflection. It is a reminder that not everything arrives with clarity, not everything is captured cleanly, and not every truth is immediate. In the quiet of the night, as this faint, fragile visitor moved through the dark, it carried with it the weight of 1,000,000 years of travel and the curiosity of millions of people watching from Earth, each trying to understand what it meant, each projecting their hopes or doubts onto a piece of cosmic debris that neither knows nor cares who observes it. And perhaps that is why the story begins with a whisper rather than a shout, because the universe rarely announces its visitors loudly, preferring instead to let them slide silently across the sky, inviting us to listen closely to the faintest echo drifting in from the stars. When the first faint reports of 3I Atlas began circulating, a wave of curiosity swept across scientific circles and online communities alike. People wanted images clear, sharp, captivating visuals that could confirm the arrival of a new interstellar visitor. They expected a release similar to what they had seen with other major astronomical discoveries: colorful composite images, detailed diagrams, and side-by-side comparisons. But 3I Atlas did not offer that luxury. Days passed, then weeks, and the images, when they finally appeared, were subtle, blurry, and heavily processed. To many, the delay felt unusual, to some, suspicious, and to others, a sign that something was being hidden. But the truth of the delay begins with the stubborn nature of the object itself and the reality of deep space imaging. Capturing a faint, fast-moving interstellar fragment is like trying to photograph a grain of dust drifting across a black room with a flashlight. You need precision, time, and the patience to collect enough photons to build anything meaningful. And that patience, in an age where people expect instant information, quickly turned into frustration. NASA's process is built on accuracy rather than speed. While the public imagines astronomers pointing a telescope, snapping a picture, and releasing it instantly, The real workflow is far more delicate. Raw space images often look nothing like the polished photos the public sees. They start as noisy, grayscale data filled with cosmic rays, sensor artifacts, streaks, and distortions caused by Earth's atmosphere. When the object is faint, so faint that it barely registers above background noise, astronomers must take dozens or even hundreds of exposures, stacking them to reveal the object's true position and shape. Each exposure requires calibration, correction, and verification. For 3I Atlas, this task was especially complex because the object was breaking apart before observations even began. This meant that the brightness profile kept changing, making it difficult to establish a consistent point of reference. Every time scientists believed they had a stable image, the object shifted again. Its brightness dimmed further, its fragments drifted apart, and its dust cloud expanded. What would normally be a few nights of imaging turned into a slow, methodical process. Another factor behind the delay was the need for confirmation. NASA, like other scientific institutions, cannot release preliminary data without multiple layers of verification. One telescope detecting a faint object is not enough. Cross-confirmation is required. Measurements must match orbital predictions. Independent observatories across the world must review and validate the detection. With 3I Atlas traveling at extreme speeds and passing through limited visibility windows, early data was inconsistent. Some telescopes saw it, others didn't. Some reported fragmentation, others reported a single fading nucleus. Before any image could be released, scientists had to be certain that what they were looking at was truly the interstellar object and not noise, not a misidentified comet, and not a processing artifact mistaken for something meaningful. The public often forgets that scientific caution is not secrecy. It is responsibility. A rushed release of incorrect data would have caused far more confusion and controversy. NASA is also bound by collaborative timelines. The discovery of 3I Atlas did not belong to one agency alone. It involved international observatories, research institutions, and multiple data pipelines. Sharing raw images prematurely would jeopardize the scientific papers being prepared by teams who had invested their time, expertise, and resources. Academic etiquette requires that researchers who gather the data have the first opportunity to analyze and publish it. This respect for scientific labor may appear like a delay to the outside world, but within the community, it is the backbone of cooperative research. While the public waited, scientists were racing behind the scenes, refining orbital paths, modeling the object's fragmentation, and determining whether it truly came from interstellar space or was perhaps a long-period comet from the outer Oort cloud. Only after these confirmations could NASA responsibly publish the images. There is also a technological side to this story. Telescopes such as Pan-STARRS, Atlas, and the Hubble Space Telescope rely on image processing pipelines that remove noise, correct distortion, and align exposures. These processes cannot be rushed. The raw images of 3I Atlas were extremely faint, often requiring advanced stacking techniques to bring the object into view. Pixels had to be aligned with extraordinary accuracy, sometimes to within fractions of an arcsecond. Even a slight misalignment would smear the object out of existence. And because 3I Atlas was not a solid point of light, but rather a diffuse, disintegrating fragment, the algorithms used for typical asteroid imaging were not enough. Custom scripts had to be written. New calibrations had to be tested. This takes days, sometimes weeks. The idea that NASA was perfecting a lie misunderstands the nature of astronomical truth. Truth in astronomy comes slowly, through repetition, verification, and collaboration. It is not like a photograph taken with a smartphone. It is built, piece by piece, from faint signals that barely pierce the darkness. Meanwhile, the passage of time magnified public suspicion. When people do not see what they expect, they begin to imagine alternatives. Online discussions turned the delay into speculation. Was NASA hiding something? Was the object artificial? Was it dangerous? Was it too strange to explain? The reality was far less sensational, but far more scientific. NASA was attempting to rescue clarity from faintness. They were working against the clock, against nature, and against a rapidly fading visitor. Every hour lost meant fewer photons captured. Every mistake meant starting over. And when the images were finally released dim, grainy, and uncinematic, they did not satisfy the expectations of those who had already built narratives during the silence. To some, the images looked like evidence of concealment, when in truth, they were evidence of cosmic distance and fragility. The delay also highlights a deeper disconnect between scientific communication and public expectation. We live in an age of instant updates, live streams, and real-time data flows, but space does not always cooperate. The universe is in no hurry to reveal itself. Interstellar objects do not pause for clarity. They come and go, leaving scientists scrambling to make sense of fleeting glimmers. NASA's delay was a product of this reality, a collision between cosmic timing and human desire for immediate answers. And as 3 Atlas continued to fade into darkness, the time pressure grew even more intense. The images needed more exposure, more correction, more verification. The scientists wanted to be certain before making any announcement. And certainty, in this case, did not arrive quickly. For those watching from the outside, the silence felt like withholding. For those working on the inside, it felt like responsibility. Between those two perspectives lies the story of why the images of 3I Atlas arrived late, and why the delay became part of the mystery surrounding the silent traveler from another star system. When people imagine NASA or any major space agency capturing an image of an object drifting through deep space, they often visualize something simple: press a button, snap a picture, receive a clear image. But the truth behind the scenes is far more intricate, technical, and almost meditative in its complexity. Deep space imagery, especially for objects as faint and elusive as 3I Atlas, requires a process that unfolds slowly, methodically, and with a patience that contrasts sharply with the fast-paced expectations of the modern world. In reality, capturing an image of an interstellar object is closer to assembling a puzzle in near total darkness, where each piece is a photon arriving from millions or even billions of miles away. And before any image reaches the public, it must endure a long journey, not just through space, but through layers of software, calibration, verification, and expert analysis that together transform raw cosmic noise into something meaningful. It starts with the telescopes themselves. Instruments used to detect objects like 3I Atlas are not simple optical cameras. They are highly sensitive arrays of detectors, advanced CCD or CMOS sensors designed to collect minute amounts of light. These detectors are cooled to extremely low temperatures, sometimes near absolute zero, to reduce thermal noise. Even with this delicate setup, the signals they capture are faint, scattered, and often drowned in background interference from cosmic rays, atmospheric distortion, and instrument artifacts. When a telescope takes a raw exposure of a dim interstellar object, what appears on the screen is not a beautiful photograph, but a noisy, grain-filled grayscale frame, where the object may be no more than a faint smudge. If people saw these raw frames, many would not even realize a celestial object was present. To the untrained eye, the data appears chaotic and disordered, but to a scientist, every pixel carries potential. To process these raw frames, astronomers begin with calibration. Calibration is the process of cleaning the image from all the imperfections and distortions introduced by the telescope itself. This includes removing bias, the electronic noise inherently present in the detector, and dark current, which comes from thermal electrons despite the low temperature. Then comes flat fielding, where scientists use images of evenly illuminated surfaces to correct for uneven sensitivity across the sensor. Dust particles, tiny scratches, or optical imperfections must also be accounted for. All of these steps must be completed before the object itself even becomes visible. For an object like 3I Atlas, which was faint, fast-moving, and disintegrating, these calibrations had to be performed with exceptional precision. Because if any step is rushed or misaligned, the object could be lost entirely within the noise. Once calibration is complete, astronomers turned to stacking, a technique essential for deep space imaging. Stacking involves taking dozens, sometimes hundreds, of exposures of the same region of the sky and layering them on top of one another. This allows faint signals to accumulate, revealing objects too dim to be seen in a single frame. But stacking is not as simple as overlaying images. Every exposure must be aligned perfectly. Stars in the background must be used as anchor points. Any shift, distortion, or rotation must be corrected. For static objects, galaxies, nebulae, star clusters, this is relatively straightforward. But for moving objects, especially fast-moving interstellar ones, alignment becomes far more complex. 3i Atlas was not sitting still. It was racing across the sky at tremendous speed, changing position between exposures. If the stacking were done incorrectly, the object would blur into a streak or disappear entirely. To solve this, astronomers must track the object's predicted motion and adjust each frame accordingly. This is known as shift and stack, and for 3i Atlas, it required a dynamic, constantly updated model of its path, but motion was only part of the challenge. 3i Atlas was breaking apart, shedding material, and creating a diffuse cloud around it. This meant that its shape was not a single point, but a spread out, evolving region of faint light. Standard algorithms for tracking and stacking do not work well on diffuse objects. Scientists had to use customized approaches, often writing scripts specifically for this event. They had to isolate the object's faint core while simultaneously tracking the surrounding debris cloud. This required iterative modeling, running the same data through multiple versions of a processing pipeline, adjusting parameters each time to refine the result. These iterative cycles take hours, days, and sometimes weeks. Every parameter change triggers a cascade of recalculations. Every recalculation updates the object's brightness, position, and shape profile. Once the basic stacked images are complete, agencies move to the next stage, data verification. This stage is less visible to the public, but crucial behind the scenes. Scientists must compare their results with independent observatories, check consistency across different wavelengths, and verify that features seen in the images are real and not processing artifacts. Interstellar objects are rare, only 3 have ever been confirmed, so the burden of proof is extremely high. Any anomaly must be scrutinized. Every unexpected shape must be analyzed. What looks like a fragment may be a cosmic ray strike. What seems like a tail may be a sensor defect. Verification ensures that when the image is finally released, it represents the truth of the object, not the limitations of the instrument. Another often overlooked stage is photometric correction. Deep space images are not only pictures, they are measurements of light. Scientists must correct for atmospheric interference, moonlight, airglow, and even the curvature of the Earth's atmosphere, which bends and distorts incoming light. For professional-grade data, every correction must be logged, documented, and reviewed. With 3i Atlas, photometric correction was particularly difficult because the object's brightness was fluctuating due to fragmentation. This meant that scientists had to account not just for external distortions, but for internal changes in the object itself. The brightness measured on one night could not be directly compared to the brightness on another. The evolving nature of the object required dynamic modeling, which takes time and computational resources. After corrections and verifications are complete, the images enter the enhancement stage. This is the part the public often misunderstands. Enhancement is not manipulation. It is a scientifically careful process of adjusting contrast, sharpening faint structures, and presenting the object in a way that accurately reflects its properties. Deep space data is extremely low contrast. Without enhancement, many objects would simply appear invisible. But enhancement must be done cautiously to avoid introducing false features. Scientists must test different enhancement levels, compare them across datasets, and ensure that the final product remains faithful to the raw information. Then comes the final stage, preparation for release. NASA and other agencies must create accompanying descriptions, explain the processing methods, prepare graphics, and ensure that the public understands what they are looking at. This involves multiple team scientists, communication specialists, visual designers, and editors. Internally, these steps can create delays, especially when dealing with an object as unique and scientifically valuable as 3i Atlas. All of these processes calibration, stacking, verification, correction, enhancement, and preparation occur behind the scenes, hidden from the public eye, but essential to the integrity of the final image. People often see only the delay and interpret it as secrecy, but behind every delayed release lies thousands of lines of code, countless hours of data processing, and the relentless pursuit of accuracy. And for an interstellar visitor as fragile and fleeting as 3i Atlas, that pursuit becomes even more intense. Because scientists know they are capturing something that may never pass through our skies again when an event unfolds far above our heads, so distant that not even the most powerful telescopes can offer a perfect view. It leaves a space between what scientists know and what the public feels. And human beings, by nature, fill empty spaces with stories. When NASA delayed the release of images of 3i Atlas, that empty space expanded, and with it grew a quiet mistrust that has become increasingly common in the modern age. This mistrust did not appear out of nowhere. It is woven from years of rapid technological change, a flood of information, a flood of misinformation, and the emotional instinct to question what we do not fully understand. In many ways, the story of why people believe NASA was perfecting a lie has less to do with 3i Atlas and more to do with human psychology, our relationship with institutions, our appetite for mystery, and our fear of being left out of the truth. Across the United States and much of the world, trust in large institutions has been steadily eroding. This includes governments, corporations, news organizations, and yes, even scientific agencies. The reasons vary from person to person. Some of it comes from real historical mistakes, moments when institutions failed, misled, or withheld information. Some of it comes from misunderstandings or misinterpretations. Some of it comes from the overwhelming complexity of modern science, which can feel distant or inaccessible to the average person. But whatever the cause, this erosion creates fertile ground for doubt, especially when unexpected delays occur. The very idea that NASA took extra time to release images triggered a familiar suspicion. If the truth were simple, why the delay? If everything were straightforward, why not show the images immediately? This reflexive doubt is not irrational. It is rooted in a desire to understand and a fear of being misled. And when combined with the mystery of an interstellar object, a visitor from another star system, it becomes easy for people to imagine that NASA might have something to hide. In the digital era, information travels faster than facts can be verified. Social media platforms amplify speculation at lightning speed. Before NASA even commented on the delay, conversations were already blooming online. Everyone had an opinion. Some speculated that 3i Atlas was artificial. Others suggested it had an unusual trajectory. Others questioned whether an interstellar object could fragment so quickly. When official images did not appear right away, many of these theories hardened into belief. And once a group of people believes in a narrative, even a small pause feels like proof that the narrative is real. Silence becomes suspicious, careful processing becomes concealment. Scientific caution becomes manipulation. This dynamic is not unique to astronomy. It happens with medicine, climate science, and almost any field where the public feels disconnected from the decision-making process. The simple truth that scientists needed time cannot compete with the emotional pull of a story about secrecy. Another layer of doubt comes from how space imagery is presented. Most people do not realize that the stunning astronomical photos they see online, nebulas glowing in vibrant colors, spirals of distant galaxies, bright comet tails, are not raw images. They are processed, enhanced, composed from multiple wavelengths, and cleaned of noise. They are representations, not photographs. So when NASA eventually releases a dim, grainy image of something as rare as an interstellar object, people feel disappointed. They expect cinematic clarity. When the object is barely brighter than the background, they assume something is wrong. To the untrained public eye, the image looks unimpressive. And for some, the mind jumps to an alternative explanation. NASA is hiding the real images, the real object, the real truth, and offering a toned-down version instead. The irony is that the processing NASA performs exists to help reveal what is real, not obscure it. But the more time that processing takes, the easier it becomes for suspicion to grow. There is also a deeper emotional layer, one that has to do with the nature of the universe itself. Interstellar objects represent the unknown in its purest form. They come from elsewhere, places humanity has never seen, carrying secrets we cannot decode. This alone creates a sense of unease. People project onto these objects their hopes, fears, and unanswered questions about life beyond Earth. When something so rare enters our solar system, people want a story that feels meaningful. They want answers that feel complete. And when those answers arrive slowly or imperfectly, the imagination fills the gaps. Doubt thrives in the unknown. It thrives in the dark spaces between information. It thrives in silence. NASA's cautious pace provides the perfect environment for that doubt to grow. Not because anyone is lying, but because humans are drawn to narratives that make sense of uncertainty. The psychology behind mistrust is amplified by the speed of modern communication. A rumor can circle the world in minutes. A scientific explanation may take days. Outrage spreads faster than patience. Suspicion spreads faster than understanding. And in this environment, when NASA delayed the images, alternative explanations found receptive audiences. Some people truly believed the agency was hiding alien technology. Others believed the object was a threat. Others believed it proved a cosmic event NASA did not want to reveal. These beliefs were not based on evidence. They were based on emotional logic, the logic of fear, curiosity, and the desire for certainty. When uncertainty is uncomfortable, conspiracy feels comforting because it offers a clear antagonist and a clean storyline. To understand why people think NASA perfected a lie, we must also look at how the human brain processes ambiguity. Humans are uncomfortable with incomplete information. Our brains are wired to identify patterns, even when none exist. In a blurry, faint image of Three-Eye Atlas, some people see structure where there is only noise. In a delay, they see meaning where there is only caution. In a lack of data, they see design. This pattern-seeking behavior is natural. It is part of what helped humans survive in ancient environments. But in the context of deep space science, it can lead to misunderstandings. When something is unclear, people will fill the emptiness with something that feels purposeful. Another powerful force behind doubt is the democratization of information. People today have access to telescopes, tracking software, orbital calculators, and online databases that were once available only to professionals. For some, this access creates confidence. For others, overconfidence. They may misunderstand a data graph, misinterpret a brightness reading, or misalign their own observations and then assume NASA must be wrong. Instead of uncertainty, they see deception. Instead of complexity, they see manipulation. This creates a tug-of-war between professional expertise and amateur interpretation, with the delay in NASA's image release serving as a catalyst for that tension. At the heart of this doubt is the simple reality that people want to belong to the truth. They want to feel informed. They want to feel empowered. When they perceive that an agency withholds information even for legitimate reasons, they feel excluded. That feeling transforms easily into distrust. It is less about NASA and more about the timeless human fear of not knowing, not seeing, not being allowed in. And when the universe sends a messenger from another star system, people want to be part of the moment, not observers waiting behind a curtain. This is how the idea formed that NASA was perfecting a lie. Not because of evidence, but because of emotion. Not because of secrecy, but because of silence. Not because NASA created deception, but because humans create stories when the universe remains quiet. When an object enters our solar system from another star, it carries with it the faintest whisper of its long journey. But unlike the brilliant comets that sometimes grace our skies, interstellar objects seldom shine brightly. They do not arrive with glowing tails or vibrant reflections. Instead, they drift through space almost unnoticed, radiating only the faintest echoes of sunlight. To photograph something so dim, so distant, and so fast-moving is to engage in a quiet scientific struggle against the very limits of light itself. And to understand why the images of 3I Atlas were so difficult to obtain, we must first understand the mysterious and delicate nature of distant light. Light behaves predictably, but faint light behaves stubbornly. When an object is millions of miles away, the sunlight that reaches it is already weak. When that light reflects back toward Earth, the signal becomes incredibly faint. And when the object is small, fragmented, or surrounded by dust, the light scatters rather than reflects cleanly. With 3I Atlas, all of these challenges converged at once. The object was faint, fragile, breaking apart, and hurtling across the sky at tremendous speed. Every physical property that could make it difficult to photograph was present. In essence, astronomers were trying to capture a dissolving speck of cosmic dust illuminated only by the dying glow of a distant sun, a task that requires patience, precision, and the ability to read signals that nearly vanish into darkness. One of the fundamental challenges comes from the inverse square law of light. This law states that as distance doubles, the brightness of an object decreases fourfold. For something as distant as 3I Atlas, even small changes in distance drastically reduce its visibility. A comet inside our solar system reflects a reasonable amount of sunlight. An interstellar object arriving from deep space reflects almost none. Its faintness is not a choice, it's a consequence of physics. And telescopes, no matter how advanced, cannot create light. They can only collect what little exists. To gather enough photons from 3I Atlas, telescopes needed long exposure times, stacking methods, and specialized filters. But long exposures create motion blur when the object is moving rapidly. So astronomers had to choose: either shorten exposures and reduce clarity, or lengthen exposures and risk turning the object into a streak. Neither option was ideal. Another complication arises from the object's velocity. Interstellar objects move faster than nearly anything native to our solar system because they are not bound by the sun's gravity until they enter its domain. 3I Atlas was traveling at tens of thousands of miles per hour. High-resolution imaging revealed multiple distinct fragments, each surrounded by a faint halo of dust and gas. The separation speeds of these fragments were incredibly small, only a few meters per second, indicating that the breakup was not explosive, but rather a slow mechanical failure. This gentle disintegration suggested that 3I Atlas was held together by extremely weak cohesive forces, perhaps the result of billions of years of exposure to interstellar radiation, which could have altered its internal structure. Over such timescales, cosmic rays can penetrate an object's outer layers, creating microscopic fractures and chemically altering ices into more brittle forms. The chemical composition inferred from its spectra also hinted at an unusual mixture of materials. Unlike comets from our solar system, which typically show a combination of water ice, carbon dioxide, and ammonia, 3I Atlas displayed an enhanced presence of carbon-rich compounds and complex hydrocarbons. These materials, while common in the cold interstellar medium, are more volatile and less stable when heated by sunlight. NASA's researchers speculated that as the object neared the sun, these exotic compounds may have sublimated rapidly, destabilizing the fragile outer crust and triggering a cascading breakup from within. In essence, the comet's own chemistry might have led to its self-destruction. The disintegration also carried intriguing implications about its age and history. The surface of 3I Atlas had likely been exposed to cosmic radiation for millions, perhaps billions, of years, slowly accumulating a hardened crust that trapped volatile gases beneath. As sunlight began to penetrate deeper layers, these trapped gases would have expanded, building pressure until the surface cracked apart. This kind of outgassing-driven fragmentation is not uncommon for comets. But what made 3I Atlas unique was the timing. It happened so early, and so violently, that it left astronomers wondering if interstellar comets might be inherently more fragile than those native to our solar system, having drifted unprotected through the harsh environment of interstellar space. Such objects could develop internal weaknesses that make them prone to early disintegration when exposed to a star's heat. Another compelling theory emerged from NASA's computational models: rotational breakup. As 3I Atlas approached the Sun, uneven jets of sublimating gases might have acted like thrusters, gradually increasing its spin rate. If it rotated too quickly, centrifugal forces could have overcome its internal cohesion, tearing it apart. This spin-up mechanism has been observed in several solar system comets, such as 332 Pika Murakami, which shattered due to rotational stress. However, for 3I Atlas, the process seemed to occur under unique conditions. Its mass, density, and shape were all unknown, and these parameters directly affect how fast an object can spin before breaking apart. By modeling various scenarios, NASA scientists found that even a small change in outgassing direction could trigger instability in a body with such a delicate structure. The Hubble Space Telescope's detailed observations provided further insight into the disintegration sequence. Images taken weeks apart showed that the fragments were dispersing along a curved path consistent with the parent body's orbital motion. This meant that, although broken, 3I Atlas still retained the memory of its original trajectory. The largest fragment was estimated to be only a few dozen meters across, surrounded by a diffuse cloud of dust extending thousands of kilometers. These fragments, though faint, continued to release material as they drifted away from each other. For NASA researchers, this was like watching the slow unraveling of a cosmic fossil, a process that revealed the internal makeup of an object that had been sealed since before humanity existed. As the fragments continued to fade, spectroscopic data revealed something even more remarkable. The composition of the released gases indicated an abundance of carbon monoxide and methane, gases that form only under extremely cold conditions. This finding supported the idea that 3I Atlas originated from a region far from any star, perhaps an outer disk similar to our Oort cloud. Such an environment would preserve fragile ices that would never survive closer to a star. If so, this meant 3I Atlas was carrying the chemical fingerprint of a place beyond the frost line of another star system, an ancient, frozen remnant of cosmic history. Its breakup was tragic in one sense, but it also provided scientists with a once-in-a-lifetime opportunity to study the chemistry of interstellar material up close. The premature disintegration also forced NASA to rethink the nature of interstellar objects more broadly. Oumuamua, the first interstellar visitor, did not display a visible coma and remained intact, behaving more like a rocky asteroid. Borisov, the second, behaved like a traditional comet and survived its passage around the Sun. 3I Atlas, however, combined features of both its interstellar origin was clear, but its fragility was extreme. This diversity among interstellar visitors suggested that they are not a single class of objects, but rather a spectrum, each shaped by the unique history of its parent system. NASA's researchers propose that while some interstellar bodies may resemble rocky asteroids, others might be composed of ultra-volatile materials that make them inherently unstable when entering a new star's environment. The timing of its breakup also carried practical implications for future missions. NASA and other agencies have long discussed the possibility of sending a spacecraft to intercept an interstellar object, but the rapid disintegration of 3I Atlas underscored the difficulty of such endeavors. Planning an interception requires predicting the object's stability over time. Yet 3I Atlas demonstrated that such predictions can be uncertain. A target that looks stable one month might fragment the next, making mission design extremely challenging. However, even in its disintegration, 3I Atlas provided valuable data that could help refine models for how such missions should respond to unpredictable changes in target structure. Another remarkable aspect of the event was how it changed the way scientists interpret light curves of distant comets and interstellar bodies. Before 3I Atlas, erratic brightness variations were often dismissed as observational errors or temporary outgassing events. Afterward, astronomers became more cautious, realizing that such irregularities might signal deeper structural issues or fragmentation. The lessons learned from this event are now influencing how observatories monitor and interpret the behavior of new discoveries, especially those with unusual trajectories or compositions. For many scientists, the disintegration of 3I Atlas was also a philosophical reminder of the fragility of cosmic bodies and the impermanence of matter itself. Here was an object that had survived unimaginable timescales, traveling across light years of empty space, only to crumble apart within sight of humanity. Its demise was quiet, almost poetic, scattering dust that would continue drifting through the solar system long after the fragments faded from view. Those particles, tiny and ancient, now joined the interplanetary medium, becoming part of the same cosmic material that builds new planets, moons, and comets. In that sense, the breakup of 3I Atlas became more than just a scientific event, it was a symbolic one. It reminded scientists and the public alike that even in its destruction, the universe continues its cycle of renewal. The fragments of one world become the seeds of another. NASA's continued analysis of the data gathered during and after the breakup has offered an unprecedented window into how fragile interstellar materials behave under stellar influence. The discovery not only expanded humanity's understanding of what lies beyond, but also deepened the emotional connection we feel toward these distant, mysterious travelers that remind us how transient yet magnificent every encounter in the cosmos truly is. When NASA scientists finally pieced together the immense amount of data collected from telescopes across the globe, they realized that 3I Atlas was more than just another cosmic visitor, it was a messenger carrying the story of another star system written into its molecular and physical structure. This realization didn't happen overnight. It emerged from countless nights of observation, careful calibration, and tireless analysis, drawing upon every corner of NASA's research infrastructure. What began as a curiosity, a faint, fast-moving object spotted by the Atlas survey, soon became one of the most significant discoveries in the history of modern astronomy. The data gathered from its composition, motion, and light patterns revealed a tale that bridged interstellar chemistry, planetary formation, and the shared origins of matter across the Milky Way. The first step in NASA's analysis was understanding what 3I Atlas was made of. Spectroscopic readings, light broken into its component wavelengths, acted as a kind of fingerprint for the object's chemistry. Every element and molecule absorbs and emits light in a unique pattern, so by studying its reflected sunlight, scientists could identify the ingredients on and beneath its surface. The spectra obtained from the Hubble Space Telescope and ground-based observatories showed features that were both familiar and strange. Familiar, because they included water ice, carbon monoxide, and carbon dioxide, the same volatile compounds found in comets within our own solar system. Strange, because embedded within those signals were traces of complex organic molecules and exotic carbon chains rarely seen in local comets. These molecules suggested that 3I Atlas formed in an environment very different from the one surrounding our Sun. The presence of these organics, especially long-chain hydrocarbons, was among the most fascinating findings. Such molecules often form in extremely cold environments, far from the heat of any nearby star, where ices can accumulate and react under cosmic radiation. NASA's scientists theorize that 3I Atlas likely originated in the outer reaches of its parent star system, in a region similar to our Oort cloud or Kuiper belt. But there was a twist: the specific ratios of carbon-based molecules and nitrogen-bearing compounds didn't match the profiles seen in comets that formed around the Sun. This difference meant that its parent system had a distinct chemical makeup, possibly indicating a star with a different metallicity or age. In other words, 3I Atlas was a physical sample of a solar system built under different cosmic conditions, a piece of another world that drifted across the galaxy for eons. Before entering ours, NASA's next major breakthrough came from studying how the object interacted with sunlight. As 3I Atlas approached the inner solar system, it began to release gases and dust, creating a diffuse coma around its nucleus. The rate and composition of this outgassing were carefully measured by instruments like NEOWISE, which detected emissions in the infrared spectrum. These measurements allowed scientists to estimate the relative abundance of different volatiles and their release rates. Interestingly, the gas output of 3I Atlas was not consistent with typical solar system comets. It showed an unusually high ratio of carbon monoxide to water vapor, implying that it had formed under colder conditions where carbon monoxide could remain trapped within ice. This reinforced the idea that 3I Atlas originated much farther from its home star than any comet we know from our system. As the quiet hum of the universe continues beyond the reach of our instruments, the story of 3I Atlas stands as both a revelation and a reflection of our growing awareness of the cosmos. It reminded NASA and all of us that the universe is not a distant spectacle to be observed from afar, but an active and interconnected system of motion, matter, and mystery. Every time an object like 3I Atlas enters our solar system, it brings with it the history of another star, another origin, another fragment of cosmic evolution that has drifted across the vastness of space to meet us, however briefly. These encounters prove that interstellar space is not empty. It is alive with travelers, fragments of creation that carry the stories of countless other worlds. Through its study of 3I Atlas, NASA did more than identify a comet. It began to understand a pattern of galactic exchange that links us to regions of the Milky Way we have never seen. It deepened our knowledge of how planetary systems form, how they dissolve, and how their remnants journey across light years to share their chemical essence with others. It showed that exploration is not just about distance, but about perspective, the ability to recognize that even the smallest cosmic visitor can hold lessons larger than our imagination. The lessons from 3I Atlas have changed the direction of modern astronomy. They have inspired new missions, new technologies, and a new generation of scientists dedicated to unlocking the secrets of interstellar space. The discovery accelerated efforts to detect these objects earlier, to prepare spacecraft capable of intercepting them, and to understand what they can reveal about the origins of stars, planets, and possibly life itself. Each discovery expands the boundaries of our curiosity and reinforces the idea that humanity's destiny lies not in isolation within one solar system, but as part of a greater cosmic continuum. Perhaps the greatest gift of 3I Atlas is the reminder that wonder and science are not separate pursuits. They are two sides of the same human longing to know our place in the universe. It is the quiet awe of looking up at the night sky and realizing that something from another star once passed silently through our cosmic neighborhood, leaving behind a trace of itself and a challenge to keep searching. In the brief light of 3I Atlas, we glimpse the endless bridge between worlds, a pathway that connects every atom, every planet, and every civilization that has ever looked to the stars and asked the same question: what else is out there? Good night.